Let's take a look at an example now of how we can use the facts that we know about inverse functions to find the derivatives at points of inverse functions. So let's take a look at this example. F of x is equal to 1/4 x cubed plus x minus 1. We'd like to find the derivative at x equals 3, or the derivative of the inverse function at x equals 3. Now, we had this fact that we just used. Now, in your mind, many of the examples that you've seen in the past about finding inverse functions, you could calculate algebraically. That was a whole bunch of it in pre-calculus. I'd give you a function, and then you would then calculate the inverse function of it. Now, that is not always either capable of being done or even easy to be done if it is capable of being done. So this is an example where you could not find the inverse function of this because you'd be trying to, if you replace this with a y, you'd be solving for x. You could not do that. So you can't find the inverse function algebraically, then simply take its derivative. So we have to use this fact up here. So what we're really trying to understand in this context is we're really trying to find this. When x is equal to 3, what is this piece here? So we'll say ddx of f prime of 3. Now, this isn't proper notation, but this at least gets us thinking about it in the right way. So the inverse function of 3, the derivative of the function when x equals 3, is going to be 1 over f prime of f inverse of 3. So I do this because I would like us to now figure out how do we find f inverse of 3. So what is f inverse of 3 equal to? So if you remember things about inverses and regular functions, f of 3 says x is equal to 3. F inverse of 3, we're really saying in this case y is equal to 3, and we'd like to figure out what x value makes this true. So if I look up here at my expression here, I'm trying to solve 3 is equal to 1/4 x cubed plus x minus 1. Now, if this is a one-to-one function, or also an injective function, that's another name for it, this is a one-to-one or an injective function, then there's only one solution, right? For every output, there's only one input. So you can go back and look at your notes about one-to-one functions. But if this is indeed a one-to-one function, which in this case it is, I just need to find one value of x that makes this true. So you could try different numbers and see what happens, but when x is equal to 2, this is equal to 3. So x is equal to 2. So what this means then is this is saying that f inverse of 3 is equal to 2. So I can plug that inside there. So this gives me now what I'm looking for, this ddx of f inverse of 3 is going to be equal to 1 over f prime of 2. So now I need to find the derivative of the function. And so this is the function, right? So we know that the derivative of f is simply 3/4 x squared plus 1. Then all I have to do now, if it's 3/4 x squared plus 1, I just plug in 2. So I have f prime of 2 is equal to 3/4 times 2 squared plus 1. Or in other words, this is now equal to 4. So this tells me now that the derivative of f inverse of 3 is equal to 1 over 4. So whatever this function looked like, then whatever its inverse function looked like, the slope of the tangent line at 3 of the inverse function is equal to 1/4. Okay. Now, notice what we're saying here is that there's a point associated with this. So we have this point here, 2, 3. So if we look back at our original function, when x is equal to 2, I have the y value of 3. So at this point here, what I have is f prime at 2 is equal to 4. So this is a point on the function. The slope of the tangent line is equal to 4. Now, when we correspond that to the inverse, remember, x's and y's are switching. So at the point 3, 2, at the inverse function, the derivative of that at 3 is equal to 1/4. So this is just the same notation up here as this. So the derivative now of the inverse function of this is 1/4. So the important thing that we could pull out from this is indeed you get reciprocal slopes. So the derivative at the function, at whatever point that is, when you look at its corresponding buddy with its inverse function, it's just simply the reciprocal slope. Which makes sense. That's really what we're doing here by taking the derivative of f and then the inverse, is we're trying to find what that corresponding y value would be for us, or x value would be here for us to plug in the derivative, and then that's it. So reciprocal slopes that we get for derivatives of inverse functions, at least the slopes, the actual numbers that we get.